In this presentation, we cover the biomechanics of the heel rise test. So in this study done in 2009 by Henriksen, they were examining an eccentric lowering compared to a concentric rising during a heel rise. And here's our graphic with the information we need to assess this activity on the right here. And what we can see is that we have 4 different kinds of data. The top data here is joint angle. This is the joint moments. The second one, tendon force, is here, and the GRF. And we'll ignore the GRF for now. And we see time on the x-axis. So essentially, as we look at the angles, we can see, okay, this is dorsiflexion, here's positive, and plantar flexion is negative. So this is the peak lowering point. So this point here corresponds to the ankle joint angle here on the left. And then this inverted peak here pointed down, that points to the peak plantar flexion point here on the right. So we can see one complete cycle of raising and lowering starts here at this high maxima. It goes here to this. This is the peak heel rise here. And then we go back to a lowering position. So this is the concentric phase here, and this is the eccentric phase here. So if we look at the external moment, it's something interesting happens as we go from a fairly deep dorsiflexion position. As we see this continuous rise into plantar flexion, there's the moment's relatively constant, and then it drops and reaches a minima at the point of peak heel rise. So just when we're unable to lift any further upward or translate our body mass upward anymore, our moment decreases significantly, and then as we lower, that situation inverts itself. We can also see that the actual tendon force created that's needed from the point of view of the external load to match that external also decreases consistent with the moment. So how is this true? So how does the external moment decrease as we go into a peak heel rise? And if the moment or the external load is going down, why can't we raise ourselves up any farther? So let's start with the external moment first. So we start with our typical equation here, and we're going to focus just on the gastrocsoleus group, not the other muscles of plantar flexors of the ankle, because they don't have, their moment arms are so small. We can notice that it's basically a second-class lever, like here. So we have a force on the posterior aspect of the ankle with its moment arm, and that stays relatively constant. And then we have a force that's anterior to wherever the ground reaction force is, and that's actually going to vary with joint position. So essentially, as we lower the foot and the ankle is perpendicular to the ground reaction force at, say, 0 degrees or slightly dorsiflexion, we can see that the moment arm for the external load is going to be longer or larger than it is when we're in peak plantar flexion. So in peak plantar flexion, the moment arm of the GRF is smallest because the ankle joint center has moved anteriorly toward the ground reaction force vector. And so because of that, that's why the moment decreases. And that's also the tendon force actually we only need enough to satisfy the external load. So if the external load goes down, then the tendon force is also going to go down because the moment arm at the ankle for the plantar flexors is relatively constant. So then why do we feel the burn when we're performing a heel rise at peak heel rise position? So during peak plantar flexion, why is that the most difficult part for us to kind of execute? Well, the other piece of it is, well, how is this affecting the muscle itself? And we know that essentially the soleus muscle is highly sensitive to length changes. And so as we plantar flex, we shorten the muscle beyond its normal functioning range, and then therefore rely more on the gastrocnemius muscles, so it shifts some load to them. And they're also shortening, although they're not as sensitive to shortening, they don't have as much PCSA. So essentially the shortening effects on these two muscles is what makes it more difficult. We can see here that heel rise height is an important variable to collect. In this particular sample is one of the studies that was done at University of Rochester. and we can see this is the frequency of heights achieved by a sample of young controls, elderly controls, and people with a flat foot deformity. And there's the percent of heel rise height that they were able to get to. So basically, this is the people that could get to a heel rise height as compared to bilateral during a single. So nobody actually got to 100% of height, but the young people, which are these stripes, more typically reached heights that were 50% or higher. And then elderly controls were almost as good, but not quite. One person only reached a height of 40%, but most were 50% to 70%. And then the flat foot deformity people would really had a hard time reaching heights above 50%. And then 2 people couldn't perform the heel rise test at all. So one thing you look at during the heel rise test is height, and it tells you about the functioning of the muscles themselves. Okay, and then we also look for repetitions. And so here's 3 different studies that looked at the average number of repetitions. This is in young athletes, this study here in 2006. Here's a study of middle-aged people, 30-year-olds. And then here's a study that across several spectrums of how they could do it. And essentially, young athletes are in the 40 range in terms of repetitions. These 30 range for this particular study. And then this last study that was done in 2005, the range is much lower, but however specific to age group. So in summary, the basic biomechanics of the ankle joint complex for plantar flexion during a heel rise test, it's a second-class lever system. The loads at the ankles can be very high because they're lifting against body weight. The concentric and eccentric components are relatively the same. So the one thing that will be different is that on lowering, there will be less neural drive to the muscle because it takes less activation to get the same force. But the tendon sees the same force on lowering as it does on rising. And then our typical assessments of heel rise performance have to do with assessing height and number of repetitions.